have to do this. So hi, welcome all. I went back to 275, Introduction to Computation. Sorry, Scientific Computing. Plop, no. Can I move over here? Yes. Okay, so here's me. You can always reach me, preferably over email. And so there's it's not a required text, but it's one of the two textbooks. And I really would like to hear which one of those textbooks, if you are using them, is useful for you. Of course, you're going to say, well, the free one's good. All right, this is going to be annoying. So today I'm going to talk about data and model comparisons. Really, this is the heart of the course. So you have data, which are typically in a physics measurements. So you have description. You have a model that this is, the physics that we're comparing the data to. So I don't know, you have a block of ice, you measure the temperature, and you have thermodynamics as your underlying theory. So you have a model how temperature should rise in that block of ice in a given room, for example. You have things like bias. These are offsets. Intentional or not, your instrumentation may have an offset. The one that I usually deal with is the night sky, where the night sky is a certain level of, in my detector, a certain level of electron level. It's never completely dark, so you have like a base level. And then whatever you see is on top of that. So there's here's 0 counts, then there's the night sky gives me 5, and the moon gives me 1500, for example. But what I'm interested in was that tiny little thing next to it, was 3 counts, for example. So bias is offsets from where you are, intentional or not. We often do intentional ones, for example, because back to that digital camera, a digital camera becomes linear if you give it a certain charge to begin with. So it starts to get anywhere between 0 and 10 is sort of nonlinear, and then after 10 until 10,000, it's beautifully linear. So you sort of give it intentionally. You flash it first, for example. And so there are biases in both data and model. And then we have error, the uncertainty, the measurement uncertainty in the data. If you think your data doesn't have error, so you've either been lied to, or your instrument looks great, but probably has uncertainty somewhere. If your data does not come with uncertainty estimates, you'll have to do it for them, or you'll have to figure out what they are intrinsically. So that's a lot of stuff that we try to work with on. So the reason that I'm talking about, it's what does this have to do with Python? Well, it's not just Python, right? This was also physics. And this is the kind of data that comes in. I talked that this class was about somebody hands you a CSV file, an Excel sheet that's a million pages long with data. Now what do I do? And so knowing what kind of data you have is critical. Has anyone heard about quantitative versus qualitative data? Right? Quantitative is like numerical. That's what we physicists think of. However, there is also qualitative data, and qualitative data is still data. And you can do the same tricks on that, right? And thus sociology was born. And so qualitative and quantitative data are both kind of information that we have. And it can be non-numerical, or you can turn qualitative data into quantitative data, for example. You try to put a number on it. We deal with the quantitative most of the time, but that doesn't mean it's not there. And so it is, if you get something and you go all right, this column's quantitative, 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 qualitative. Okay, this is how the, lab assistant felt while they were taking these measurements. So these things are important to immediately classify your data in. Here's a thing that is very easy, is a trap that's very easy to fall into, and even trained scientists will do it, especially on Twitter. And so multiple anecdotes isn't equal to data. Anecdotal evidence is not quantitative, and there's survivor bias. There's a lot of survivor bias, right? So multiple anecdotes is still not data. The plural of anecdote isn't data is another way to say it. Anecdata is sort of where you start going a couple of times, is there something to it? It is sort of, this is a motivation to go look for quantitative data, not this is the end all. A guy in the pub told me that this was not true, is just not going to work against hopefully scientific results. So the data types that we can have are nominal, also called categorical. So basically, if you read about this, these are labels for groups. You go, well, I'm never going to get that, right? Or I'm not labeling birds. I'm not a biologist. We deal with nominal data all the time, especially in machine learning, right? That's a lot of nominal data. Ordinal, the order of the data has meaning, but the actual numerical difference does not, right? This is something that doesn't have a 0 point. Can you think of an example? Whoever came first in the hop sack race, right? That's the kind of thing. That's ordinal data. It doesn't matter in what, like, that one of them took it in 5 minutes, the rest took it on an hour and a half. It's just that the first one gets the pie, and then so forth. So that's ordinal data. We use that all the time as well in our lives. Interval is the step size actually matters. So the scale matters, but it doesn't have a 0 point. Now, this is the kind of data that physicists would hate, because yes, it has a scale. It's the kind of thing like I'm 5 paces behind the next runner, but it has no 0 point, right? It's a relative measure, and like the next runner is 20 paces behind me, like, but everything's moving. What 0 point are you talking about? So interval data is a kind of thing that you'll get a lot, and it has no 0 point. And the first thing you'll tend to do is go like, all right, where's the 0 point, or can I give it one? But often it won't have. So the step size is important, but the 0 point is not there. And then the ratio is the interval scale with a true 0. That's what we think we get all the time, but it's not the case, right? We often get versions of this, and we start treating it as ratio data, which interval data, for example, is you can have, oh, the thermometer is broken. It actually reported temperatures, and we can see it went up in the afternoon and then went down. But the 0 point's completely busted, right? We can actually tell that the 0 point's off. This happens, though, basically broken instrument, but still data. Can I still use this? So calibration sort of gets you from interval to ratio. And really, calibration can get you from ordinal to interval to ratio, for example. But it's very important to figure out which kind of data you're actually dealing with. So I'm telling you all this so you can take, like, you get the data, you can take a step back. It's like, all right, which one's quantitative, which one's qualitative? Is it nominal, ordinal, interval, or ratio? This is why I'm telling you these different kinds. Because if you're in physics land, we always think in this, but it's not always this kind of data. And especially if you venture outside, you get these other kinds. We still happily assume that everything is Gaussian for every kind of data, but that doesn't mean that's necessarily proven in a mathematical scale, on a mathematical sense. So, error. This is not the same as a mistake, right? So this is error has a very specific meaning, rather than say, oh, you've made an error, right? That's terrible, everybody. It is the inevitable uncertainty in a measurement. That's how we talk about errors. If your data doesn't have an error, you didn't bother noting it down. It definitely has, right? I talked about this before. Think of it as if all else fails, your measurement will have thermal error, because the whole thing has a temperature, and so whatever you do, you have an uncertainty. I don't know if any of you do woodworking, but it's the kind of thing like, how well can you actually cut a piece of wood? It's the kind of thing where it's like, well, I can measure down to 1/8 of an inch, right? I've been here long enough that I actually can measure things in inches now. Yeah, I'm doing everything in centimeters, and that's a good way to get a headache here. And so you can sort of measure, it's like, well, you can get within an 1/8 of an inch, because the little thing at the end is, my eyes aren't perfect, so it's like, yeah, 1/8. But then how good can I cut it? About within 1/8 of an inch of where I put the little mark, right? So my uncertainty in that is about a Gaussian with a width of 1/8. If I cut a whole bunch of 2x4s in like 2 foot lengths, because I'm building something, they're within 1/8 of an inch, which is for building construction perfectly fine. I think actually 1/4 of an inch is acceptable, which is okay. But if you get down to like the woodworking with like people who make cabinets, for example, or beds, that kind of accuracy, they frown on things like 1/8 of an inch. So you need to have better measurement equipment. So they invest in things that actually measure down to the 16th or 32nd of an inch, including better saws. So that's how you should think of as the error. The error is like, to what degree do I know this? Like, what's the spread in values if I try to? So this is not an error. Well, it is an error in the normal English colloquial sense of the word. Somebody made a huge mistake, which basically was not hitting the brakes. I was sort of really impressed when I saw this. Nobody was hurt. I like the examples where nobody was hurt, miraculously. But so it is a systematic. It's also, so you've got systematic error and random error. The thing that I just talked to you about was random error, the uncertainty in the measurements. Systematic error is another phrase for bias. Systematic error is if you measure a whole bunch of 6th graders, but they were walking on a little pedestal, so turns out you all have like 5'4" 6th graders, which that doesn't work. That doesn't compare well to national averages, for example. You're going to go like, I have Miracle Grow 6th graders, or I accidentally introduced a bias. Right, so systematic errors are the kind of things that will really sort of raise after you compare to an other data set. Random errors should be in there, right? So you can actually get it out of the data set itself. Can you see how we're going to use NumPy for this kind of stuff, right? So that's why I'm talking about data now. So the offset, systematic error, the bias, a fixed offset, an intercept at a fixed value, for example. Suppose you do the weight versus measured weight. My scale is off. I think that often. And so here my scale is off. And so if I actually put the cat on there, it's not actually a kilo. It doesn't go all the way down to 0. Right? So mechanical scale, the thing is a little busted. So everything is off by a certain amount. So the data is now interval data. See how fast we drop from ratio to interval data? Or 0 point busted, something was off, it's off. We are now dealing with no longer ratio data. It's not a fixed 0 point anymore. Or it's not a 0 point where it should be. You can think of it as maybe as ratio data, but off with a bias. You can also have multiplicable. So the first one is easy to recognize because you go like, well, it should go through 0, and if it doesn't go through 0, something's wrong. This one's much harder because you're usually trying to figure out what the inclination is. So this is harder to figure out where it's not that the scale wasn't calibrated to get back down to 0. It's that the spring inside has actually lost some of its springiness. And so I now can sit on there with much more weight and not actually get, or my relay can be much higher, but it's actually giving me a much higher value. This is, I think, what's happening with mine. And so the slope rather than normalization, this is the thing that you're after. And it still looks okay because it has like the 0 point where it should be. This is so much harder to pick up because you want to know the slope. And often if you have an effect, you're looking at the slope. So if there is a multiplicative effect, that's harder to calibrate. You might have to use a bunch of weights. And then you have the random error, the noise. This is what happens on a hot day, this is a cold day, right? So this is the kind of thing where it's like you have some sort of noise in your measurements. Your measurements aren't always perfectly on the line unless you have a much more accurate measurement instrument. By definition, we do not go to the laser rangefinder for our wood cutting, right? You can cut your house down to 30/2 of an inch, but why on God's green earth would you? Because you don't need to, right? All the brackets are made to have like a 1/4 inch of you're basically making more work for yourself. So you use the equipment that's appropriate, and that's time and money-wise makes sense. So all measurements have an uncertainty. We just pick the measurements that we need for, and we sort of minimize the noise to the degree that we can afford to. So this is a good example of that. the Hubble constant is the slope of the distance between the recession velocity. So that's the slope we're interested in. And the scatter around it is about 10%, just from various physics, etc. Getting it down to 1% is now a major scientific operation that includes recalibrating everything and lots of Hubble observing time, right? So that's a lot of effort to get it down 1 order of magnitude in uncertainty. So it usually is like, do you need that, or can we get what the slope is from just more points? So the first thing you do is like, well, we already have this equipment. We can just add 100 more points and see if we get the slope that way. So there's sort of a cost-benefit analysis there. There's a random S in there. Okay. So we have the Gaussian distribution. This is the most common distribution assumed for a random process, the bell curve. So this is what we use for uncertainties. If it's a random process, the random scattershot noise, it should follow a Gaussian distribution. So if you look at your own data and you subtract the model, what if you were left with looks like a Gaussian distribution, you're good. That looks like that was a good assumption then. So anything random, including people. And so this is what you then can say about the noise, right? So you have, this is where my measurement should be. So let's say that's where the model is. And I'm 1 sigma, 2 sigma, 3 sigma away from the model. The scatter says that there should still be, you know, almost a percentage point a little bit further than 3 sigma. So that's not, as soon as you see this is something that is really important to understand in the scientific method. It's perfectly fine to be 3 sigma away from it if you have 1 data point out of 100. That's like, that's fine. It still adheres to the model. Only 70-ish percent, so 69% has to be within 1 sigma, which means that you have quite a bit of outliers. There's a whole book called Outliers, and then we go like, think about like what these means. Like, well, maybe that was a hot day, or just, you know, whatever scatter you have. You can think of it as like, well, this is what you would do on the test, because, you know, we're in school, well, university, and so this is where, you know, you would do well on the test. These are bad days, these are good days, so this is sort of like the amount of random caffeine plus I slept well kind of scatter. So that's sort of the random noise around where you expect it to be, but you expect quite a range, and it's one single outlier is not telling you anything. So you use the 68, 95, and 99.7 rule. So all our data should lie within plus or minus 3 sigma, which is, you know, usually a band around a model, and then you can still get the occasional outlier. All right, precision versus accuracy. So the reason that we call it scattershot or shot noise is, well, this is how we think of it, right? It's the target. This is the model where we want to be on. So we have low accuracy and low precision. It's just all over the place. And so we have low accuracy, the model, high precision. So we're sort of grouped all here. And this is high accuracy and this is high accuracy. So we're definitely where we want to be, but there's low precision, like we're still scattered around it. Which ones of these kind of data is useful to actually compare to a model? Sorry, that's what I'm asking. Whoop. So, what helps your science? Low accuracy and high precision. So, I'm nowhere near, but I'm well off. This actually does nothing for you, because it looks like it's very accurate, but there is some sort of bias happening. So it's very hard to figure out why we're doing this. The high accuracy and high precision, that's the, you know, of course we want to be here. And because we want to be here, that'll never happen. And so the high accuracy, low precision, actually this is something that we can live with. Because I can add like 20 more points and I can figure out where the center lies, right? So that's fine. It's something I can live with, and especially, this is something you can kill off with lots of data. Like lots of similar low precision, but you know, since you're on the model, you're good. Low accuracy and low precision, yeah, back to the drawing board, your experiment doesn't work, right? So there are some options that you can use. This is good, and then this is fine. And usually, we're in fine. Like sometimes you design an experiment and the cosmic microwave background, for example, the temperature that they measure for that is the error bars were smaller than the line that they drew, right? So then you're in this range and you're like, everybody can stop arguing. This is the temperature of the universe. We're done. If like 7 or 8 significance. So, but usually you start with this and then you move to that. This is bad because it's biased. This is just nothing. So don't go figure out what other instrument you need for that. Okay, so good example for that is where like give people coordinates. And I love these XKCDs because it's like he's clearly nerded out on how many precisions after. And you will hear this from hopefully every physics class. Hopefully. Give me the unit, because otherwise I have no idea what you're talking about. And the second is, how many digits of precision do you actually know this? And this is a communication thing, right? Because, and this is why this is funny, at least to me it's funny. You start with like, I have, 28 doing something space related. Basically, I'm trying to hit the right continent. This is, you're pointing at a specific city, like that's within 1/10 of a degree. You're pointing at a neighborhood if you add one more digit, and then particular, so this is the kind of thing that you probably can just about see on your GPS. Particular corner of a house, this is the kind of GPS that we don't have access to, but other people do. And the funny thing is, if you want to be at this level of accuracy, you need to take into account not just the diffraction of the air, but you are also you have to take into account the curvature of space because of the Earth. So we're getting to that level of accuracy. Now it's a specific person in a specific room. People think we're at this accuracy. No, there's a limit to how accurate you can do GPS. You're pointing at Waldo on a page. So basically you're now on unphysical numbers, right? Hey, check out the specific sand grain. We're definitely not there. And either you're handing out raw floating point variables or you build a database to track individual atoms. Either case, please stop. So it sort of gives you like, I think this is a good example to sort of like, to what degree do you actually do this? Because NumPy will happily report this. And if you stop thinking, a couple of cells earlier, you'll tell me this is the answer when I ask you this, right? So that's the difference I want you to understand here. I mean, it's very easy to sort of, because, it's in the computer's memory. It's sort of, this is all random, but you can report it like that. And the thing that I do a lot as a referee is go, this has 8 significant digits. Does it? I still come. You can't stop thinking about how many significant digits do I actually know this? Not just because the computer spewed it out, but what was the actual input here? All right. So the bias or systematics is a shift in your values. Something adds +1 to all your, like, I don't know, your Arduino's acting up or something. Certain values are structurally missing. The 100 Fahrenheit values above that are just never reported. Multiplicative, scale on your thermometer is completely wrong. So these are things to be aware of. If you think your data doesn't have stuff like this, you've missed it. Congratulations. So it is the kind of thing that either plotting it up as a visual, modeling it, or simply going, are there not a number of values in there? These are data sanity, cleanliness kind of checks that you need to do before you start happily modeling away. For example, who has heard of the term survivor bias? Yeah, okay, so there's a plot with a plane that has the measles. This is where this comes from, right? So World War II, they were doing the Brits have a lovely word for that. A boffin was plotting where planes had holes that came back, right? So these are the planes that came back, which means that if you put a hole anywhere here, or anywhere here, you apparently lost a critical part of the plane didn't come back. So the answer was, where do you put extra armor? In where planes have, lose the ability to come home. Although if you see some of the pictures like I started with, it's amazing with what kind of holes they did manage to fly all the way home. So this is the kind of thing, survivor bias is something that happens a lot, and this is where anecdotal evidence comes back to bite us. So startups, for example, everybody heard of the one startup that made it. Okay, cool. What's the normalization of that number, right? Was there one startup in all of Louisville that made it, or were there 500 startups and one made it, right? The odds are completely different with those numbers. So startups, professional athletes, college professors, these are all kind of the kind of profession where they go like, oh yes, well I did this, so clearly that's the way you should do it, right? Yes, but you don't hear about the other part of your data. And your data can be like that, right? You only get a measurement if you measure, for example, the size of butterflies that come back from the Great Migration, right? So this is the kind of stuff that that's something I can measure. It's something I can easily measure from pictures, so it's definitely something I want to do. Except you're measuring the ones that got here. So was there something about their size that they didn't make it? Do you need to be a certain size butterfly to actually fly all that way from Mexico here? Or, so you have to sort of reconstruct the missing part of that data. And so survivor bias, it can mean that are there certain conditions to be met so that I can make the measurements? And if my measurements are below a certain level, I won't be even able to make them. In astronomy, we're plagued with this stuff because basically, oh, we're interested in faint galaxies. Congratulations, we'll never find them beyond, very, very nearby. So everything that we look at further and further away, my God, that's a monster. That must be the age of monsters. I'm like, no, it's like it had to be a monster for us to even see it. Otherwise, we won't see it at all. So it's called Malmquist bias because a Swede figured it out, but it is still a survivor bias kind of thing. You will drop below your detection limit, and there is a population below that detection limit. So all of this stuff goes to NumPy arrays. Later, it might go into Pandas data array, data frame, but all the NumPy tricks work on data frames as well. So NumPy array, list of number strings or any available type. So we can put any kind of data in there, and we can put multi-dimensional, right? So it's not just, doesn't have to be a matrix. Usually we load up a table, so it's really just a matrix of numbers, but it doesn't have to be. I have multiple data sets that are of NumPy arrays that are three-dimensional, for example. So there's like 2 positional and 1 frequency array. And then if I change that over time, I've got a 4-dimensional array. So, welcome. And so, but if you want to have those basic values of your data, we can run through NumPy and give us mean, mode. I realized I sort of skipped over mean and mode last time. Mean, median, and mode. Do you know what those are?
Mean is average. Median is like if you had a list of all the numbers, all the unique numbers, it would be the middle. Or is it every number in whatever term is directly in the middle, even with duplicates?
Median throws out an extreme. So you throw out an extreme value. The mean is the average. And the mode is the one that occurs more. This is the kind of thing that I also always have to give myself a beat to think about, like which one is, but it depends on which is being reported. It depends on what kind of distribution you're looking at. And so I realized that I should spend some time on that because different things are reported. But you can generate NumPy arrays, so NumPy zeros, ones, and empty are kind of gives you a way to populate an array immediately. So instead of doing I'll allocate all this memory space immediately, NumPy basically goes, okay, you want this amount of space, and I'll allocate it as you start telling me what needs to go in there. So, and so you can have ones or zeros, and then you can start manipulating. So it's a very quick way to start your own data. If you want to model images or 3-dimensional data or something like that. The best part about NumPy is that it also has a random module, and I really love this bit because it's a built-in function that gives you good random values. And if you think random values are hard to get, you should talk to a mathematician. they've been working on that since World War I in order to get good random but predictable values. So they act like a random numbers, but they come out of this formula. And you can already guess what you would use that for. We both have the key and the formula, and crypto is based on this. And you probably heard the word crypto. So you can say, I have a Gaussian distribution. Give me 100 random values from that Gaussian distribution. I have this log normal, and I want 10,000 values out of this. So this is a good way to sort of add that Gaussian noise to pretend it has an uncertainty to data, and also give you so you can put realistic noise to images, so to your data. And so, for example, if you're building a camera, you want to know if that actually does everything you want it to do, so you can generate your fake data first, do the whole analysis on it, and say, well, if it actually works, if the specs work as advertised, we should be able to do this. This is a big part of science now, where you go like, all right, well, we've run through the whole simulation, we've run through the whole thing. It's sometimes a little more complicated than this, but I wrote a paper not too long ago where I just used NumPy random and like, okay, well, this is the measure that we're expecting, this is the width of the distribution, and then, can we actually see it with this telescope? And the answer was, yeah, a few. So that was kind of neat. But it was just this, right? It was just, this is what I expect, add reasonable noise or distributions to it, and then see if you could still falls within your detection envelope. All right, random numbers. They're useful. It's weirdly hard to do well. So, and it's not just for shot anymore. So you can use it for things that have like a tail or have like a weird distribution. And so, yeah, I always put in random noise generation. So it's the kind of thing that underlies a lot of crypto, basically encoding. But the built-in functions, there's a lot of them, so I'm not going to go over it. But basically, if there's a distribution that you've heard of in quantum or what have you, I think it just rolls through a whole bunch of values, or no? If it actually, yeah, there you go. So there's a whole bunch of built-in distributions. So it's the kind of thing where if you hear in statistical mechanics, for example, this follows a exponential distribution, you can literally just put it in here and go like, here's the two values that set what that distribution is, and I'll draw 10,000 examples of it and then see what that looks like. So I kind of, I love memes and stuff like that, right? You get data, sometimes you get some extra information, so that's sort of like, this has 3 pieces of information. Next things up. Insight means that these 2 things are important. Wisdom means that, hey, they're connected like that. And everybody who's tried to paint a unicorn on is a little bit further along. But the thing is that we have this data. It should give us insight, but half my job is I have new data. I'm trying to figure out why it's not telling me anything. And usually it's because there's a hidden bias somewhere, there's more noise than I thought, something like that. Figuring that out is tricky. So here's a thing that I use a lot, yet I would like to emphasize caution here. NumPy as array allows you to turn a list into a NumPy array. This is wonderful because you had your list, it built itself with a pen somewhere, and like, oh, I have a list of numbers. These should be numbers. And so if I do NumPy, here's my list, d-type float, I'm saying force this as a float. Do so with care, because you've now, if there was a string in there, NumPy just went, you told me this was a float, and a float it is, so here you go. So the problem may persist between keyboard and screen, but miscasting happens, right? So just because you can put it into a NumPy array doesn't mean you should, or there's, it can go wrong horribly. The mix of strings and floats will be interpreted as floats with this, right? You told me this, and I will dumbly do this, and then you'll get the weirdest values because I'm not exactly sure how that process works. So with a NumPy array, you have a couple of things. These are basic built-in functions like static deviation, mean, and mode. So those things pop right out. So if it's a Gaussian, you have the mean and the mode, you have the center of the value, and you have the width of that distribution right away. I use this all the time. So you can get the basic statistics of your data, of a column of your data, immediately. And we keep using these things, even if we're at pandas and we get new data. So that's sort of what the first thing you do. If you go, this should be Gaussian, right? I already made this joke. Because you've probably seen these. I love it because it kind of shows like, yeah, any random process is pretty close to that Gaussian distribution. And little balls falling through a distribution of pegs is always going to be, there's noise around it. That's the shot noise, right? So, but it follows a Gaussian distribution pretty well. Yeah, it's a good physics toy. And so you can sort of see what the random process is, right? The random processes, they bounced against each other. And they bounce against all of those little rods. And so it's rare that you bounce all the way over here, then you sort of fall straight down. So that's always the one that people use to show this is the random distribution. But a random distribution is what like a Gaussian distribution is what we assume if it is truly a random process. Like if it's a confluence of a bunch of different things like wind, temperature, how much your heart's beating, that kind of thing. Or in this case, I think this is archery. And then, so if you have a bunch of different small influences, they sort of become a random pattern. Here, come on, there you go. Yes, numbers is not the interpretation, right? That's the next part. And honestly, that's the part that I don't teach a lot here because we're talking the numbers, we're putting it into a plot, and then things, right? So weighted random number generated produces a bunch of numbers. Let's build it into a narrative, right? So this can also say any speculative nature paper, but the interpretation can mean different things. Yeah, I know this meme is now so old. The people in it I think are retired. But the thing is, the mean will be shifted a lot if you have one massive outlier. And so a big difference between mean and median sort of tells you immediately my data for the size of my data sample, I have one outlier that's messing it all up. You can have things where you have like mode and mean, for example, are massively different. It's like, oh, there's a tail distribution of there. And that's going to skew anything I do with it. Any standard deviation is going to be skewed by that kind of thing. So it does tell you things immediately. And I cannot overemphasize, like the normal distribution is assumed to be a good description of random processes. That's true for single or completely independent variables. Like I just said, temperature and wind speed, for example. However, as it turns out, everything is connected with everything else in a sort of like loose pattern. So that's where this goes out the window. That's later down the road, but this is usually what every physics experiment that you see goes, oh, cool, here's a bunch of random things. That's a normal distribution. Fantastic. We report our values as plus 1, 2, or 3 sigma around it. These are symmetric errors, right? The temperature was 110 Fahrenheit plus or minus, 0.5. Plus or minus, right? So that error is completely symmetric around that measurement that I gave you. In modern physics, you can sometimes get it was plus 0.8 and minus 0.3. That's a non-random, like there is something where it's like, yeah, we actually know our instrument does this weird thing where it suddenly goes one way. And that's so we still sort of report where the 68% lies, but it doesn't have our measurement value immediately in the center. It's skewed. All right, that's later down the line. We can still deal with that, right? That's okay. But this is sort of like, welcome to 19th and 20th century physics. Like, all of it was assumed to be this. And 90% of the time, I don't know, making that number up. But most of the time, this works just fine. Okay. So, who here has heard of the p-value? Okay. Social and medical studies love this stuff, right? This is we boiled down how significant our result is down to one number. So, here is the most likely observation. This is the distribution of possible observations that we can make. If it's here and the leftover of that, that is the p-value. So it is really the fraction, how many sigma outside you are, the fraction left that this could possibly been a random occurrence. So I sort of think of it as the odds that this have gone wrong because all the various little uncertainty measurements sort of conspired to give us something that looked like it was real, but it isn't. For reasons that I am not entirely sure, now the rule is that 0.05, so 5% is significant. So 2 sigma result. Below 0.5, it's a significant result. This is relevant for if you ever write a scientific paper or read a scientific paper. If people say significant or highly significant, it is below that value. Yes, this is an XKCD, but he's accurate in this case, right? He's also accurate about the other ones where people start saying on the edge of significance and all the other things, right? So highly suggestive, I've been there, and hey, this looks interesting, maybe you should have a look, right? The thing is, this is a sliding scale. And rather than say, oh, here's the magic number, magic numbers are never a good sign in science. So we can just have a sliding scale. You can report what the p-value is. There is a 10% chance that this was a random occurrence. There you go. But you can only really use the word significant, highly significant below that number, right? So it is tied to the kind of language that you can use around it. So statistical tests, so before I go, the statistical tests often report a p-value. So you, for example, you've measured 30 elementary school kids, and you have one that's 6 foot, right? And you go like, all right, compared to the rest of the distribution, here's 6 foot fourth grader, and then here's the rest of them, right? And so what are my odds that was random? And so, well, that probably has a good chance of being, significant. So I report significant find of a high, monstrous fourth grader reported. But it is the kind of thing that you have to say, this is the odds that I accidentally, blindly did not measure everybody in fourth grade, but accidentally included a teacher. So that's the kind of thing that you have to do with a statistical test. The statistical test tells you what the random error tells you could have been, influence of errors, and then so uncertainties sort of conspire to give you a random event that looks significant. So p-values are reported a lot, especially in social science and in medical science, but there's now a bit of pushback against that whole, this is the boundary that you're allowed to, below this allowed to publish, above that, redo, because there's something called p-hacking, which is essentially rerunning the statistical test or a different statistical test until you have a p-value that's just below the magical number. This is why I think it's better to go, this is the p-value that we have, this is the significance, here it is. So, another few things that we can do with NumPy arrays. We can set conditional arrays, where is none and is inf. Again, we're now cleaning up our data. Select data where this particular statement is true, right? Where T is below 100. So it's like, give me all the temperatures below 100. But you can also select all the pressure measurements where the temperature was below 100 Fahrenheit. Is none and is inf. Is none is not a number. So if not a number was reported, essentially this is an empty cell. You can check for that. And you can also say, hey, did we accidentally divide by 0 somewhere? And you can say if that's an infinite, if any of the ones are infinite. So you can go like, all right, drop those, remove those. So those are things that you can check in your data set. And if you think that doesn't happen, oh, yes, it does. So this is a good way to check for those things. I always end up having to throw a couple of rows away because there was, a poor measurement in there. Oh, fantastic. I seem to have gotten that whole 50-minute lecture down pat. So we talked about Python syntax, Jupyter Notebooks. Never mind that part. And so we'll do the third Jupyter Notebook today, or Friday. And we're going to start playing with random. So now you know where that random stuff comes from. We'll definitely use it if we start making our first data and then fitting a line through it, for example. OK, so Friday we work on assignment 3. I know assignment 3 had some of the things in there already. Thanks for letting me know, but as I said to the rest of the group, I can only mess up in your favor. Please run over it anyway and then turn it in. All right. Yeah, any questions about data, ordinal versus et cetera? OK. Yeah, sorry to get a little philosophical, but knowing what kind of data comes in is sort of the step 0 of data science.